Hello and welcome back to Math and Tea, the show where we talk math and drink tea. I'm your host, Dr. Joseph Vandehei, and in today's episode, we're returning to answering that question, what is math? And today we're also going to be taking a little bit of a look at that additional question of why is all of this strange, abstract, gobbledygook kind of stuff we've been talking about actually useful? To do this, we're going to talk a little bit about where mathematical problems actually come from. There's kind of three main ways in which mathematical problems arise. First, some non-mathematician gives us a problem and says, hey, solve this. The second way is that we take one of those problems and we generalize it. And the third way is we kind of just keep studying an extant mathematical problem. And for discussion, let's call these interfacing, abstracting, and deepening. Let's start with interfacing, which is where a mathematical problem arises from a non-mathematical source. There's lots of ways this could happen. For starters, plenty of mathematicians work for non-mathematical employers. For example, the NSA, AT&T, Google, NASA, the National Weather Service, Amazon, UPS, every single Wall Street trader you've ever heard of. Anywhere there's a need to optimize, to do things faster or more accurately, there's probably going to be a mathematician involved, and we typically refer to these mathematicians as working in industry. In an academic setting, those who work most closely with other scientists are typically referred to as applied mathematicians. Those who aren't applied are sometimes referred to as pure mathematicians or theoretical mathematicians. Applied mathematicians work with scientists in a variety of different ways. Sometimes a scientist will send a mathematician a problem and, well, it's so easy we can solve it the same day. Sometimes we can at least figure out how it's supposed to work and realize we can work through the details in a couple of weeks or months. Sometimes, however, it's so hard that we can't do it. But the reality of applied mathematics is far more complicated than scientists ask, mathematician answer. Consider the Higgs boson, whose recent discovery was a big success of the Large Hadron Collider. The Higgs boson was first conjectured to exist in a mathematical model that was trying to fix some glitches in physics. And it wasn't for decades that engineering was able to get to the point where we could actually build an object to detect the Higgs boson and support the model with actual data. Next up, abstracting. This is where we take one of those scientific mathematical problems and turn it into a more abstract theoretical mathematical problem. Part of the reason why we do this is because those scientific problems can be very narrowly tailored. A scientist, for example, might be interested in all the possible crystalline structures that can be made out of chemicals X, Y, and Z, whereas a mathematician might say, well, why do we need to care about those chemicals in particular? That's in part because we like talking about general properties of systems, and it's very hard to talk about general properties of systems when the system is so darn specific. So we generalize. This is very similar to what we talked about in the previous episode, except instead of changing our axioms to move from a space to a slightly different space, we're using it to move from a small space to a larger space that includes that small space as an example. This can be really useful to a scientist because if they come back later with a similar but not quite the same question, it's possible we've already got it solved. This process doesn't need to stop after a scientific problem has been generalized to a slightly larger mathematical problem. We can keep abstracting and abstracting and abstracting and abstracting and abstracting until we've developed a whole field of mathematics. One of the areas I work in, ergodic theory, arose from a very simple question relating to statistical mechanics. Finally, we come to deepening, where one mathematical problem leads to another mathematical problem. And this is probably where a lot of mathematical work is done these days. Sometimes, like abstracting, it's a matter of taking one problem and moving it just a little bit over to a slightly similar, but not quite the same place, because we're really trying to get down at why things work. What was it that made it work in this case that will or won't make it work in another case? Sometimes new mathematical problems come from data left behind by solving previous mathematical problems. We look at an object, maybe it has a bunch of things to it, we prove something about it, but then we notice a strange pattern in it, and we try and prove that pattern because it tells us a more nuanced and detailed and complex fact about the original object. A great example of this comes from the prime numbers. Go back 2 millennia or so and you meet Euclid. Remember him? And Euclid proved that there are infinitely many primes. Great. But then we start asking other questions about this set of data that we now have, about all these prime numbers that we have. Are there infinitely many primes of a specific form? Like, are there infinitely many primes that are one more than a multiple of 5? Like 11 is one more than 10. As it turns out, there are infinitely many primes of this form, and of many other similar forms, but this wasn't proved until the middle of the 19th century. And then we can ask another question. What about primes that are one more than a perfect square, like 5 is 1 more than 4, which is 2 squared? Well, sad to say, we still don't know. Now let's get back to that question we started with. Why is all of this useful? A person, maybe you, might look at interfacing, abstracting, and deepening and conclude that only interfacing has any practical value. And, well, you'd be wrong. Applied mathematicians don't just solve problems out of the ether. They're often using techniques that have been built up over decades or possibly centuries by abstracting and deepening other problems. I tend not to think of industry or applied mathematicians as the only ones who work on problems that affect your life. I think of them more as the ones who work on immediate applications, the things you'll see affecting you in the next year or two. Pure mathematicians, such as myself, don't expect to change the world tomorrow, but we wouldn't be surprised if we change it next century. And the truth is, well, look, we're really bad about actually knowing what is and isn't going to be useful. I mean, we're just terrible about it. Go back a century, and everyone thought prime numbers were the most useless thing imaginable, but we kept studying them because they were aesthetically beautiful. Today, we use primes all the time. You're probably using them right now without even realizing it, because primes are one of the ways we keep data secure on the internet. But I think a better defense of the usefulness of modern mathematics comes from how it expands our notion of what is mathematically possible. Put simply, we don't know how to solve the things we don't know how to solve. Or, we don't know what we don't know. Oh gosh. Okay, so what I mean by this is that there's a tendency in mathematics to think of the things we can currently do as being all the things we'll ever be able to do with mathematics, and if we can't solve something now, we'll never be able to. So let's hop back a moment. Remember how I was talking about primes that are one more than a perfect square, and how we don't know how many there are? Well, why the heck not? We've been studying primes for 2 millennia. We know tons of things about primes, but we don't know that? Why the heck not? So to me, that suggests that there's something out there. There's a new technique, a new ability, a new way to do mathematics that will help us solve that problem, and we don't have it yet. But if we keep searching, maybe we'll find it, and who knows what else it will help us do. Next time on Math and Tea, I hope to wrap up this series. I'll be talking a little bit about what it is that the typical mathematician does on the typical day. But that's going to be all for now, because I'm out of tea again.